Hey guys, my name is William and I'll be your speaker today. The topic that we will be covering today is Fractals and Dimensionality Part 2. If you haven't watched Part 1 of the series yet, please be sure to check it out right here. Before we begin our main topics for today, let's review some of the topics that we've discussed in Part 1 of the Fractals and Dimensionality series. Fractals are shapes with patterns that recur at progressively smaller scales. Remember that scaling symmetry applies to all fractals. Dimensionality, another very important concept that we went over in Part 1 of this series, is a ratio of change in detail to change in scale. Or call that dimensionality, or D, equals log n over log s. In this case, n represents the number of smaller and self-similar figures that are needed to create a specific iteration of the fractal. S, on the other hand, represents the current iteration of the fractal. N and S have to be positive integers, while D only has to be a positive rational number. So how do we tie this all together? How does dimensionality actually relate to fractals? Well, the dimensionality of a fractal determines its complexity of change on a specific iteration. The larger the dimensionality, the more complex the change would be. Now, moving on to our focus for Part 2 of this Fractals and Dimensionality series. In this lecture, we will apply calculations of geometry and algebra on fractals. For geometry, we will use the concepts of area and perimeter, while for algebra, we will use sequences and series. The fractal that we will be focusing on today is a sample fractal that I talked about in Part 1 of this series, the Koch snowflake. After we solve some sample problems on the Koch snowflake together, I will also talk about how fractals can be applied to our daily lives. Now, let's move on to the actual lesson itself. Here is a diagram of the first few iterations and the eventual pattern of the Koch snowflake. You guys now have 20 seconds to derive a basic pattern of the Koch snowflake for each iteration. Time starts now. As many of you have probably already noticed, the pattern of the Koch snowflake is that 3 times 4 to the n-1 equilateral triangles that are 1/3 shorter in side length are added to the Koch snowflake on the nth iteration. Alright, now let's move on to our first question. Calculate the perimeter of the final iteration of the Koch snowflake. You only have 5 seconds and time starts now. Okay, now that 5 seconds have gone by, let's try to solve this problem together. But can we actually calculate the perimeter of the final iteration of the Koch snowflake? The truth is, no, that is not doable.
What is this man doing?
For every iteration, the length of each side of the Koch snowflake is increased by 4/3. Hence, for the nth iteration, the perimeter of the Koch snowflake would increase by 4/3 to the nth power. Thus, since the perimeter of the Koch snowflake increases by a ratio that is greater than 1 for every single iteration, we can conclude that the perimeter of the final iteration of the Koch snowflake is divergent and would eventually approach infinity. Therefore, we can't calculate the perimeter of a Koch snowflake. However, can we calculate the area of the final iteration of the Koch snowflake? This is a yes/no question and you have 5 seconds to decide. We absolutely can calculate the area of the final iteration of the Koch snowflake. However, since this isn't an easy task, I will be solving this problem with you guys. Before we move on to actual calculations, here are some hints that you should consider. This diagram is a representation of the Koch snowflake when it is divided up into different sized equilateral triangles. So when you visualize the Koch snowflake by looking at different sized equilateral triangles, you can consider these two questions. What is the formula for the area of an equilateral triangle, and for infinite series, how is sum calculated? Keep these two questions in consideration while you solve the problem. Now, you guys have 30 seconds to derive a basic plan of attack for this problem. Remember these tips and think about how we can calculate the area of the final iteration of the Koch snowflake. Here's the solution. We will be using two variables, n and sigma. N represents the number of... Dude, I just looked at the script and I already forgot what it represented, bro. N represents the number of iterations, while sigma represents the side length of the equilateral triangle from the first iteration of the Koch snowflake. Let's begin by listing out a basic equation. Since we're trying to find the area of the final iteration of the Koch snowflake, n must approach infinity. We already know that 3 times 4 to the n-1 equilateral triangles are added per iteration. However, the area of those newly added equilateral triangles will be 1/9 of the area of the equilateral triangle from the previous iteration. As seen here, root 3 over 4 times sigma squared represents the equilateral triangle area. The 1 represents the very first iteration of the Koch snowflake, while the infinite series that is added to it represents the other iterations. Now, when we simplify this, we get the term on the bottom. As you can see, now we have an infinite series with a common ratio of 4/9. Since the common ratio presented here is less than 1, we can use the infinite series sum formula to calculate the sum of this infinite series. The infinite series sum formula is given by a1, the very first term, over 1 minus r, the common ratio. In this case, a1 would be 1 and the common ratio r, as we already know, is 4/9. Keeping this in mind, we could further simplify this term. Eventually, the calculated area of the Koch snowflake would be 2 root 3 over 5 times sigma squared. And that is how we use geometry and algebra to calculate the area of a Koch snowflake. Now that we've covered calculations, let's move on to how fractals can actually be applied in real life. First of all, as seen in all these photos, fractals can be easily observed in natural habitats. Inherent self-similar patterns that recur at a progressively smaller rate can be seen in trees. Inherent self-similar patterns that recur at a progressively smaller scale can be seen in tree branches, leaves, and waterfalls. Fractal-related computer programs are also used for climate and weather predictions. An example of this is that fractals can be used to model the spread of forest fires and prevent deaths. Fractals are also applied in health and medical services. As seen in the diagrams above, fractal patterns appear in cancer cells and in human lungs. Similar to forest fires, health conditions can also be modeled with fractals. However, these technologies are still currently in their developmental stages. Last but not least, fractals can be seen in economics and in the stock market. As seen in these diagrams, stock patterns over large periods of time can be bigger copies of their smaller self-similar iterations. As seen in these diagrams, stock patterns over larger periods of time can be bigger copies of their smaller self-similar iterations. Hence, fractals and magnified patterns could be used to predict stocks. Although stocks might seem unpredictable, we can find patterns in the chaos with the help of fractals. We're also doing a video on chaos theory, so stay tuned for that in the future. Now, let's sum things up. In the first part of this lecture, we covered calculating the perimeter and the area of the final iteration of the Koch snowflake fractal. We know that the perimeter of the Koch snowflake diverges to infinity, and that the area of the Koch snowflake could be calculated with sequences in series and a simple manipulation of the area of an equilateral triangle. We also learned that fractals are actually very applicable in daily life, more than we usually think. Fractals can be applied to nature and climate circumstances, health and medical services, and economics and the stock market. Well, I hope you guys learned a lot about fractals over these 2 episodes. Thank you for attending today's lecture, and we hope to see you in future videos.